Here in the data display, there's a rectangular plot that was inserted, and that contains the spectrum. For harmonic balance, when you have nodes such as V out, you simply select that node, and then you can add it, and you'll be prompted for the format. In this case, it's dBm. And here you can see our initial tone. That's the fundamental of 1 gigahertz. That's about 7.38 dBm output. And then the other harmonics, the second, third, fourth, fifth, sixth, and seventh. So there's our 7 tones. And for the waveform, you can always take harmonic balance data and you can use a transform that you see here, and then it gives you the waveform. Finally, there are 2 equations here for transducer gain and power gain, and again, using V in and V out, you can make calculations. So this is the basic harmonic balance results, the spectrum with the amplitude, the time domain waveform using the TS function on V out, and also equations that give you power. Now let's look at our other example of swept power and XdB. And here's the other design, swept power. Notice that it's the same circuit, the same amplifier, with a P1 tone source and a harmonic balance controller, but also the gain compression controller, which is from the simulation palette here, simulation XdB. It's right there. And looking closely, you can see that the source is set up power equals dBm to watts RF power. This is a variable. So a variable was inserted down here, and it's titled RF power equals 0. It doesn't matter what you set it to because it's going to be swept, and it's swept in the harmonic balance controller. Notice the sweep tab shows RF power minus 30 to 10 in steps of 1 dBm. So this is a sweep with 15 harmonics, and you'll get that data. But the gain compression, or XdB controller, which is also harmonic balance, requires 2 ports for the input and the output, and that's what you see here, 1 and 2. And that's why we have a 50 ohm termination here instead of a resistor, because it has to have this num equals so we can specify. That's port 2 and that's port 1. And so this harmonic balance simulation controller knows that these 2 ports are going to be the input and output, and then it can calculate the 1 dB compression point. That's what this means, gain compression, the number in dB, 1 dB, for 1 gigahertz, 15 harmonics. So 2 ways to sweep the power. One is automatic, one is where you specify it with a variable. Let's look at the results now. The data display for this example has a lot in it, but I've zoomed in here to the plot of gain, which is an equation. To write equations in ADS, you simply insert the equation here, and then you can type it in. In this case, gain equals, using the function dBm, the argument here in parentheses is V out, and you can simply do that by selecting from the contents of the data set and then inserting it into the equation. So we take our V out node, bracketed 1, which means our fundamental tone, and subtract RF power, which is our variable. And you can see the sweep from minus 30 to 10 here, and then the value of gain. Having 2 markers here, we show the difference being 1 dB. So these are the harmonic balance results with the swept RF power. And here from the XdB simulation controller, a list was inserted, and then from that list you select out power and in power, and then you have approximately minus 7.6 and 9, the respective values in dBm of the sweep for 1 dB of compression. And this concludes our video of harmonic balance and gain compression, or XdB, in ADS.